So actually for this problem, we have the VS graph describing the motion of a motorcycle as shown in this picture. Okay, we would like to know the AS graph of the motion, and we would like to find the time mean for the motorcycle to reach the position of S equal to 400 foot. Okay, actually it is this type of problem is maybe for the real case. That's the actual case that we may file when you go to for some you have some responsibility to check out the velocity of the vehicle on the highway. Okay, for this is related to our work also, because we are civil engineer, right? We working with about many type of civil work. That is this is the for the case of the highway motion problem also. So for the case that we would like to monitor the safety from the transportation on the highway. Okay, we may install the velocity camera. Okay, you know velocity camera, right? So for this case, we may install the velocity camera here. That is station 1. Okay, and after that we have the second station. Okay, that is a velocity camera. It's maybe this this we have the second one, and we may have the velocity camera here again. And for each station, we may have the equivalent distance, that is maybe this S1 and this S2 or something. Okay, so for this case, when the vehicle is moving for pass through the camera that we set up, okay, so then we can capture the velocity for the position 1, right? Okay, that is we have V1 and S1. Okay, and for the second position, we have V2 and S2, right? And for the third position, we have V3 and S3. So that's why for this case, we do not have the data for velocity and time. We have the data for velocity and distance instead. Okay, so that's why we have to understand the relationship, how to change the relationship from VS to AS and back to VT and AT again. Okay, so for this problem, this is the basic one to solve. Okay, and actually the solution is already half from the textbook, and I capture the solution here. Okay, we already know the relationship between V and S. Okay, so for this case, we know that at the first range, that is S from 0 to S equal to 200, the relationship between velocity and this 10 is equal to 0.2 S plus 10. Okay, so for this case, the problem is given us for the function, but actually if the problem is not give us, okay, so we found that it is the linear relationship. The equation, the function of V of S is easy to determine because we know two coordinates, right? It is 0 and 10, and this point is 250, right? Okay, so we know that it is the linear graph. So from the linear graph, we know that y equal to mx plus c, right? And for this case, c is the y-intercept. So then it means that c become 10 now. Okay, and for m is equal to what? M actually is equal to delta y by delta x. That is delta y is what? For this case, delta y is 50 minus 10, right? And divided by delta x, that is 200 minus 0. Let's become 40 divided by 200. That is equal to what? Which is should be 0.2. Okay. Okay. That's why we know that v is become 0.2 s plus 10. Okay. This is from fundamental mathematics. Okay, we have this equation already. Okay, and for the second part, the velocity is become constant. That is equal to 50 meter per second. Okay, so we use the relationship that actually we familiar with. ds by dt equal to v, right? And we know that dv by dt equal to a, right? Okay, so from this equation, if we rearrange this equation into dt equal to ds over v, right? And this is also, we have dt is become dv over a. Okay, so when we combine together, so then we have ds over v equal to dv over a. So then we have the new relationship, that is a ds equal to v dv. Okay, so for this relationship, if we have the as graph, we can create the vs graph. Okay, and also if we have vs graph, we can create the as graph also. Okay, so it's a little bit different with the relationship between as at, vt, and st. Okay, so from this relationship, if we plot st graph, okay, we found that slope is equal to v, right? Okay, for st graph, and for vt graph, okay, slope is equal to a. This is directly to a because dv by dt is equal to a. And the area, okay, integrations of v dt is become delta s. Okay, this is a change in position. Okay, so this is the area under the curve. Okay, in the same manner of AT. Okay, we found out the area under the graph AT is become delta V, right? Okay, but for the case that if we have the relationship between AS and VS, it is not directly related to VA and S like this. Okay, that is may for the student that study this topic at the first time, it maybe have a little bit confused because we familiar with AS, AT, VT, and ST. Okay, so if we consider this relationship, okay, when we integrate both sides, okay, if we integrate both sides, this is from V1 to V2. This is made for S1 to S2. Okay, on the left hand side, it's become the area under the curve. But on the left hand side, on the right hand side, we have this term. You see that it is not equal to v anymore. It's become v squared over 2. So then on the right hand side, it's become the difference in v squared over 2 minus v1 squared over 2. Okay. So then for this case, the area under the AS graph is not exactly equal to delta V, but it's equal to V squared over 2 from V1 to V2 instead. Okay, that is one thing that we have to remind ourselves that it is not same as AT. Okay, if we see for AT, the area under the graph is become delta V, directly become delta V. But for this case, it's not equal to delta V, it's become square term like this. Okay, in the same manner, for the case that when we take the derivative to this term, we get A equal to V dV by ds. Okay, so for this case, it means that if we have the relationship of V and S, okay, so in comparison with VT graph, we found that for VT graph, the slope is equal to A. But for VS, the slope is not directly to A. It's not exactly equal to A. It is not. Okay, but it's equal to the slope dV by ds. It's just a part. It is the slope of the graph. But if we would like to find acceleration at this position, not this time, at this position, at S, at any S, we have to multiply the velocity at that point again. Okay, so then when we would like to find the AS graph, okay, we cannot take the first derivative to VS graph and use it directly. We have to multiply it with the velocity at that point again to change it to be A. Okay, this is a little bit different, but if we understand this, okay, we may can convert the VS. We may try create the AS graph from VS graph by this step. Okay, so let's take a look for this case that we know that we have VS graph here, and we can separate into two parts. Okay, so at the first part, when S is less than 0 and less than 200 feet and greater than 0, this is in this range 0 to 200. Okay, we have the velocity function is equal to this. Okay, so according to the relationship of ADS equal to VDV, okay, we found out A equal to V dV by ds. Okay, so it means that for A equal to V is here, and dV by ds is the first derivative of velocity function. Okay, that is become 0.2 rate. Okay, and after that we multiply it to this equation, we got this. Okay, and for the case that when S is equal to 200, okay, the velocity is become 50. Okay, it's become 50 for this case. And for that, when we determine for acceleration, okay, acceleration is equal to V dV by ds. Okay, for V equal to 50, is come from when we substitute s equal to 200 into here, and it means we get v equal to 50. Okay, that is equal to this. Okay, and after that, when we would like to find the acceleration here, this is the velocity at that point, and the first derivative of velocity dv by ds when s equal to 200. Okay, that is the result for the case that if the position is in the range of 200 feet to 400 feet. Okay, we have the velocity of the constant one. Okay, so the term is become v is equal to 50, right? And take the first derivative to this term that is a constant. So then this term is become 0. So then the acceleration here is become 0. Okay, but for the case that when s is in this range, okay, we got acceleration that is equal to v. We have the same, the last function, the velocity function that we already have, and dv by ds is actually is equal to 0.2 is become here. Okay, and this is the a for the first case. We use this to value plotting the graph. For the first part, a is equal to 0.04s plus 2. Okay, so then when we substitute s equal to 0, we get a equal to 2. And when we substitute s equal to 200, we get a equal to 10, right? Okay, and for second period, that is from s equal to 200 to 400, we know that a acceleration in this period is 0, because it's moved with a constant velocity. Okay, so then that's it. We can complete the acceleration as graph here. And for the time that we would like to find, for the time, that's what is it? Okay, so we starting from the first period, that is s is greater than 0 and less than 200 feet. Okay, we have the velocity function here, and for this case we know that ds by dt is become v, right? And so this case we rearrange this equation again, we got dt equal to ds over v, but we know v in terms of s here. Okay, and when we integrate this term, we got this function. Okay, because we integrate from t equal to 0 to t equal to t. Okay, and on the right hand side, we integrate from s equal to 0 to s equal to s. Okay, so for this case, we can integrate this term and we get the time consuming from change position from s equal to 0 to s equal to s. That is this term. Okay, and when we substitute, when s equal to 200, that is the final range. Okay, we obtain time equal to 8.05 seconds. Okay, and this is the initial condition for the second segment of motion. Okay, we consider the second segment, that is s is greater than 200 feet and less than 400 feet. Okay, and we know that the velocity is constant. Okay, we get dt equal to ds over 50, right? Okay, and after that we integrate both sides from time equal to 8.05. Where it come from? It's come from this. Okay, and when s equal to 200 meter, okay, After we integrate both sides, we have delta t here, and now we have this term. And after that, we can substitute, uh, rearrange this equation again. We got t is become here. Okay, so therefore, for the case of s equal to 400 feet, okay, so then we have time equal to 12 seconds. Okay, let's complete this problem. Okay, so do we have any question?